Thanks for the kind introduction. I want to talk about fast projective skinning, which is our very fast physics-based skinning approach handling arbitrary set conditions. So first of all, I would like to give you an overview about existing skinning approaches. The most common ones here are probably linear bend skinning and dual skinning. For those you need proper skinning weights, those can be computed automatically, but usually if you want to get the best results, you let them manually painted by an artist. Those methods are very fast, but don't support dynamic effects and have no collision handling. And you run into certain artifacts. For linear bend skinning, it's a candy wrapper artifact, and for dual turning skinning, you get unwanted joint bulges. You can also use an example-based method, like for example, the simple model of low point colleagues. Here you need a lot of training data as input, but those methods can also be very fast. You can also train dynamic effects, and you can also avoid somehow certain simple collision cases. You can also take a biomechanical model of the human body and put it into a physical simulation. Physical simulations tend to be very slow, but you can get very sophisticated dynamic effects and collision handling if you do it right. When we presented projective skinning last year, we wanted to have a method, a physics-based skinning approach that needs a very small amount of input. So here we just need a triangle mesh and a simple embedded skeleton. We want to be real-time capable, support dynamic effects, and handle simple local collisions. When I say local, I mean collisions that can be pre-computed in proximity of joints, for example, in the elbow or in the knee region. And now I would like to show you how we improve both speed and quality of the method and are now able to handle arbitrary set collisions. In fact, we are the first real-time skinning approach handling global collisions of the full character. Okay, I will start with an overview about projective skinning, so our previous method, and then go over our extensions to it. So in projective skinning, as I said before, you just need a triangle mesh of your skin and a simple embedded skeleton defined by joint positions and their hierarchy. From this, we automatically compute a volumetric representation of our skeleton, and now we need some correspondences between skin and skeleton. We initialize those by nearest neighbors and correct this result by an iterative smoothing approach. And in the end, we can use those correspondences to shrink our skin onto the volumetric skeleton. And we end up now with two representations of the same skin, the shrunken one and the original one, and both share the same topology. And we can now take a triangle of the shrunken skin and its corresponding triangle of the original skin. This defines a volumetric element that can easily be split into three tetrahedra that can now be used for simulation and collision detection. And if we want to animate the mesh, we simply do forward kinematics and move along all shrunken skin vertices with their corresponding bone parts. And if we add constraints for each tetrahedra that they try to be as rigid as possible, we get our full simulation. So again, we take a triangle mesh, embedded skeleton, define our volumetric representation, and are now able to animate the character. Using projective skinning, we were able to animate a full character with about 60 to 80 FPS. But usually if you are, for example, in a game-like environment, you have a very limited time budget, so this must be faster. And we wanted to implement this on the GPU. So the GPU has the advantage that it can run thousands of threads in parallel compared to just about 10 on the CPU. So here you have to think about parallelization. And we use projective dynamics for simulation, and most steps in projective dynamics are very easy to run in parallel. But the complicated part is here, solve global linear system. So the system matrix A here is constant, so on CPU what you usually do is you pre-compute a Cholesky factorization, and then solving the linear system ends up with doing forward and backward substitution, which both are very fast, but also very sequential. So you cannot do that easily on the GPU. So on the GPU, we switch to an iterative solver. We use preconditioned conjugate gradients here. And here, instead of forward and backward substitution, you do multiple matrix vector multiplications and inner products that are both easier to run in parallel. And we first tried to use existing implementations of precondition conjugate gradients, but all turned out to be slower than the CPU forward and backward substitution. That is because those systems are optimized for very large systems with millions of unknowns, and here we have medium-sized problems with a few thousand unknowns. So we developed our own custom-tailored precondition conjugate gradients approach, and I would like to point out 3 different steps that are important here. The first thing is we had to optimize our sparse matrix vector multiplication. Second, you have to think about kernel reduction. Each CUDA kernel call introduces some overhead, and especially for medium-sized problems, these overheads are not negligible. So you have to think about fusing as many kernels as you can to avoid this overhead. And the third thing that is important is always memory coalescing, which means cache-friendly memory access on your GPU device. I would like to give you one example here for optimizations, our sparse matrix vector multiplication. So if you store a sparse matrix, you usually do this in compressed row storage or equivalently in compressed column storage form. And if you perform matrix vector multiplication, each thread acts on one row of elements. And you see 2 problems here. The first one is that each thread operates on a different amount of elements. And if you run it in parallel, then you can just be as fast as the slowest one. And your memory access won't be coalesced. So coalescing here would mean to store your elements column-wise instead of row-wise. And this is solved by the LPAC format. Here you use 0 padding to store your elements in column-wise order. Now your access will be coalesced and is thus faster. But you have to store and to read those additional zeros here. And there are other formats, but all have to store additional data, or you have to use multiple kernels to perform the sparse matrix vector multiplication. So we developed our own format that combines the ELL format and this compressed row storage format with a special access pattern, and that is able to perform the sparse matrix vector multiplication in just one kernel and has to store additional data. And it is faster than the other 2 formats and also faster than the sparse matrix vector multiplication implementation of fusebars. So if we now combine all our optimization steps, we can be up to 16 times faster on the GPU compared to the previous CPU implementation. So now we are able to simulate a mesh with more than 400 FPS. But the problem here, your meshes will usually have more than 4,000 vertices. So that brings me to the next topic. That's called upsampling. So you want to visualize a very high resolution mesh, but turns out that you don't have to simulate those high resolution meshes because your scaling will be very constrained. So you can simulate on a very coarse mesh, and then you transform your result to the high resolution mesh, and this is called upsampling. We used a method before that is called normal displacements. So you pre-compute in rest pose displacements from your high resolution mesh to the low resolution one, and then you reapply those displacements in deformed pose. And the problem here is that if you have a flat region in rest pose, and then you bend it, this bending is not well reproduced by this normal displacements. So we switched to a moving least square spaced approach. So think about a patch of your simulation vertices in rest pose on the left hand side, and the same patch in some deformed pose on the right hand side. And what we now try to find is a transformation from left to right. And if we have a high resolution vertex corresponding to this patch, we apply the same transformation and get its deformed pose. So again, the transformation transforms from rest pose to deformed pose. And we could approximate this with an affine transformation, so 4x4 matrix multiplied to this extended vector here. And I will call this pi I for short notation. This has to hold for all vertices of our patch, so we can now optimize for A and get this result here. And as I said before, now we can apply that to the high resolution vertex and get this result. It looks a bit scary, but if you think about which of those variables are dependent on deformed pose, then you can see it's just one, it's just x at prime. And all other variables here are just dependent on the rest pose and can thus be pre-computed. So you end up with a very basic, very simple updating rule for your upsampling. And this method is not new, but before it was developed for using vertex displacements. And for displacements, you have to read and store more data, so it will be slower. And we developed an approach that works directly in vertex positions. What is also slow is if you have to recompute your normals of your high resolution vertex, of your high resolution mesh. So we developed a similar approach for upsampling normals. So you can also use this very simple updating rule with some other weights, MIG, here for upsampling your normals. And those are very easy, can be pre-computed, very easy to run in parallel, and just add a minimal amount of overhead to your simulation. So we have a third extension here, but to explain that, I will show you the result first. So this is a simulation. For example, in this pose, if I zoom in and I do the upsampling, you can see it's a little bit better than before, but also this banded region cannot be reproduced very well from the new method. And if I overlay the simulation result, you see that you lose some volume. And the problem is that those affine transformations that we use for approximating the transformation cannot reproduce this bending very well. So we extended the approach for handling, for doing quadratic version that handles this banded region much better, and we don't lose any volume here. Okay, and in this way, we can simulate on a very coarse representation of the mesh and upsample to the full resolution. And this just produces 1 to 2% of overhead to the full simulation, to the projective dynamics simulation. Okay, now the fun part, collisions. So let me motivate that. I show you one pose in linear bend skinning and Euroquaternion skinning here. You can see the artifacts, left candy wrapper, right joint bulges, and also the torso looks not very nice. If I do that with projective skinning, it gets better. Torso is better, elbow is better, shoulder is better, but you have your arm inside the mesh. And if I handle global collisions, this looks better now. So we want to handle global collisions, but the problem here is that we have to add and delete constraints to our solver. And on the CPU, we use this pre-computed Cholesky factorization, and each time we add or delete constraints to our solver, the global system matrix changes, so we have to update our Cholesky factorization, which is computationally expensive. But now we have an iterative solver, and this is no longer dependent, so we can simply add and delete constraints on demand and do something like this, for example. Or another one. And do that without collisions, it looks much better on the left-hand side. I exaggerated the pose a little bit, but you get the point. Okay, you can also do something like that, for example. And without collisions, it looks very static. Or if you like, you can play like on a drum in your own body. Or for the advanced level, another one. Cannot imagine how long I've been watching this already. Okay, this is some motion capturing result. It's not this Wycon, it works. And the best thing is, we are still more than 3 times faster than originally on the CPU without any collision handling. So we can now simulate the full character with more than 200 FPS and with collision handling. And due to our upsampling, we just have to look at the left column here, because we can upsample with almost no performance loss to higher resolutions. And this is not the best we can do. We noticed that we can use fewer iterations of our projective dynamics solvers, for example, and we can also not update our collisions in each frame, but for example in each second frame or each third frame. And in that way, we can go up to 2000 FPS for a full character with no collisions, or up to 500 FPS with collision handling without any loss of quality. Okay, that was very fast. That was my talk. If you would like to try it, our code is on GitHub, so you can just download it and try it out. I think it's not working at the moment for Windows, but for Linux. But I will fix that when I come here.
Thanks a lot for the very nice presentation. I can confirm that it was out of the box in Linux. Thank you for giving the code online. Do we have questions? Yes. Go ahead.
Should I?
Maybe I should keep one. Yeah, sure.
I've got a couple of questions. One is, what preconditioner are you using for PCG and how many iterations do you run?
We use Jacobi preconditioner, so inverse of diagonal, and 10 iterations in each frame.
Okay,
so but we have multiple projective dynamics iterations, and that will...
So it's global, for the global standard.
Yes.
And for collisions, what collision detection are you using?
We use point and tetrahedral tests on a spatial hashing grid, so but on the CPU. So this can be improved if you would run it on the GPU maybe, but it was simpler on the CPU.
And what do you do about the armpits and places where you have like a sandwiching collision? Do you also solve collisions there?
Yes.
It's all over the body, you're solving collisions?
Yes.
Okay, thank you.
So we do a little bit special treatment for the hands, because here, if you do a symmetric collision, then your fingers will go out of the mesh, so we make them a little bit stiffer so that the hands can penetrate deeper into the body. So there we have a little bit special treatment, but all other parts just work.
Thank you.
So I was going to ask some of those questions that were just answered, but one remaining one I do have is, one of the biggest advantages of projective dynamics is that the matrix is constant. You're not taking that much advantage of that here. So did you compare it to a method just like using Newton's method for the elasticity instead?
Using which method?
Just like computing the full stiffness matrix and converting that.
No, we did not compare it.
Oh, and the other thing is, do you use like 30 FPS time steps, or the time steps smaller than the frame rate?
Okay. No, we just take one simulation step as we use a time step of. You can use any time step, but we do not convert the time step to the real-time computation. If you mean that. So if I have a time step of 1.5 seconds, I would take one frame, and you know what I mean. So we did not take that into account.
Thank you.
Okay, maybe we can take one more question, and we will have to move on.
Hi, are there any special considerations that have to be made to handle dynamic LOD reduction, for example, in games?
Dynamic what?
Level of detail reduction. So a character using the skinning method that's, for example, far away from the camera, we want to reduce detail.
We didn't do that, but you could do it with the upsampling. Maybe you just upsample to the half resolution, for example.
All right, thank you. Thanks again.